So what we've been talking about is ways to use trigonometry to understand problems arising in terms of location of points in the plane. And we've talked about points in the plane like Cartesian coordinates so far, x and y axes. But a useful thing to have is to consider the x and y axes as representing real and imaginary axes for a bigger class of numbers, complex numbers. So we could take for the axes of real numbers and imaginary numbers, where imaginary numbers arise as solutions to the equation x squared equals minus 1. Now x squared equals minus 1 has no real numbers as solutions, but we can invent a number, allow a number as a solution, which we'll call I, with the property that I squared equals minus 1 to be a solution to this equation. And that generates the complex numbers. Numbers of the form a plus bi, where we're going to look at combinations of real numbers a and real numbers b as coefficients of this new imaginary unit I to combine to locate points in the plane, so that the plane will represent not a real and not an x and y coordinates, but an axis for the real part, for the x of it on the real axis, and the imaginary part calibrates the coefficient there to measure in the vertical direction, so a vertical axis. So x plus y times I would correspond to the point in the Cartesian plane with coordinates x, y, but it is a single number in this bigger number system, the set of complex numbers that we're going to use. So we've been seeing translations between complex numbers and between real from rectangular coordinates to Cartesian coordinates and back. How about conversions from the x and the y to a polar representation of the complex numbers? So we'll think about an angle theta as we did for polar coordinates, and the distance here for r as what we'll call the absolute value of the complex number z, and write absolute value of z in terms of x and y. So here is the way to line things up. Z, the complex number z with real part x and imaginary part y. We'll write the x part as the polar representation of the horizontal distance, and the imaginary part y as the polar representation of that imaginary distance. And then we could express z in this form, from the Cartesian form to the polar form. And if you collect terms in the polar form, z is r times cosine theta, and factor out the r from the second term times I sine theta. So this expression cosine theta plus I sine theta is a useful thing for specifying a direction of where the point is aiming in the complex plane, and r as specifying how far out along that point you go. A very natural analog to the polar representation of a point with Cartesian coordinates. And we can keep track of this for a value of theta somewhere in the interval between 0 and 2 pi, and that's plenty to indicate any possible direction from the pole out, from the center of, from the origin, from the point 0 in the complex plane out, and that is called the argument of z. So you'll see this word before. If you're talking about the complex number z, you would specify the argument of z, and that's the angle that it makes. and you talk about this value r, which is the absolute value of z, sometimes called the magnitude of z. So let's set up a problem. Plot the point corresponding to a particular complex number, minus 3 plus 4i, in the complex plane, and write an expression for z in polar form. So let's see, minus 3 plus 4i. So we want to go over 3 units in the horizontal direction, the real direction, 1, 2, 3 units back, takes me to minus 3. 4i is 4 units up. So 3 units over and 4 units up puts me right about here. And that would be the location of the point z, minus 3 plus 4i. And now to write this for z in polar form, what we want to do is to think about it in terms of an angle theta. So z would be equal to r times cosine theta plus I sine theta. Cosine theta plus I sine theta, and r is the magnitude of z. Well, this is a 3, 4, so it would be a 5, 3, 4, 5 right triangle, and the magnitude, the distance out along this line, would be 5 units. And now cosine theta plus I sine theta. And to say more than that, we should say what the angle theta is. And what's relevant about theta is that we're going 3 units back and 4 units up. So theta has a reference triangle with side opposite 4 and side adjacent minus 3. So theta is the angle whose tangent is minus 4/3. If you want a specific value for that in radians or degrees, you can ask your calculator, but that is the angle that's determined by the complex number as it's given. Why would you want to write things in polar form? Well, it turns out that polar form makes some operations of arithmetic lots easier. The process is captured in this theorem. Suppose you've got 2 complex numbers, z1 and z2, and the complex numbers are available in polar form. So z1 has a magnitude and an argument, and z2 has a magnitude and an argument. So that's what they look like in complex form. Then z1 times z2 can be calculated this way. You multiply the r's, so r1 times r2. The size, the magnitude of the product is the product of the magnitudes of the factors. And here's the neat part. The rest of it, the cosine plus I sine of some angle, depends on the sum of the angles that were the arguments of the original complex numbers. So theta 1 went with z1, and theta 2 went with z2, and it's theta 1 plus theta 2 that is the argument of the complex number z1, z2. In the book, they go through the construction, and it's really quite a pretty thing, that if you multiply those complex numbers, z1 and z2, just using the rules of complex multiplication, what pops out for theta 1 plus theta 2 in cosine and sine is the sum of angles formula for cosine and for sine, so that the trig with the complex multiplication gives that as the way of calculating a product of complex numbers. And it also has a version for division. If you multiply by multiplying the absolute values and adding the arguments, then you divide by dividing the magnitudes and subtracting the arguments. So for example, if z is 4 times cosine 40 degrees plus I sine 40 degrees, and w is 6 cosine 120 plus I sine 120, we can calculate z times w by doing 4 times 6. This is the magnitudes, and then cosine of something plus I sine of something, and the something there is the sum of the arguments. 40 degrees for z, 120 degrees for w. So 160 degrees is the expression for A. And for B, to do the quotient, the rule was you divide, so 4 divided by 6, you divide the arguments, and you subtract, you divide the magnitudes and you subtract the arguments. So it's cosine plus I sine, and what goes there is 40 minus 120. 40 minus 120, so that's 4/6 is the same as 2/3, and it's cosine of 40 minus 120 is minus 80. Well, cosine is an even function, so cosine of minus 80 is cosine of 80. And I sine 40 minus 120 is minus 80. Sine is an odd function, so instead of sine of minus 80, it's minus the sine of 80. And you could write the answer that way for B. De Moivre's theorem is a way of using this polar representation of complex numbers to quickly calculate powers. What it says is, if you've got a complex number written in polar form, so r times cosine theta plus I sine theta, then you can write the power, the nth power of that complex number this way. You repeatedly apply that polar multiplication rule. So you multiply z times itself n times by multiplying the size of z, the absolute value of z times itself n times, and you adjust the argument of the power by adding the angle to itself n times. So De Moivre's theorem provides a much more convenient way to calculate a power of a complex number than actually multiplying out binomial after binomial after binomial, which is how you would have to do it if you wrote the complex number in Cartesian form.